Hello, welcome to Northern's Craft. Today we are going to talk about IC engine, air standard Otto cycle, air standard diesel cycle, and air standard dual cycle. So first we need to understand what is IC engine. So IC engine is a heat engine. It's a heat engine. It's a heat engine that converts converts chemical energy into mechanical energy. So it's a heat engine that converts chemical energy into a mechanical energy. Or we can say the engine works by burning a fuel air mixture in a combustion chamber to create a high pressure gas which then powers the engine part. Or we can say it is an engine which works by the fuel air mixture combustion in combustion chamber. So basically what happens in this is intake number 1, then compression number 2, then combustion, then exhaust. So what happens is intake, compression, combustion, and exhaust. These are the 4 stages in which works in the IC engine. A high pressure gas produced by the combustion pushes the piston. High pressure gas will push the piston, which is connected to the crankshaft, that converts the pressure into the rotational motion. So what happens is high pressure gases will push the piston, which are connected to the crankshaft. This further results in rotational motion. Basically, the IC engine works on fuel such as hydrocarbon fuels, in which hydrogen and carbon fuels are used in this, like gasoline, diesel fuel, natural gas, or ethanol. So basically, these are of 2 types. IC engine are of 2 types. IC engines types. Number 1, spark ignition engine. Number 2, compression, ignition, diesel engine. So IC engine are two type: spark ignition engine and compression ignition diesel engine. So basically IC engines is mainly used in vehicles, generators and industries. So what we see in the vehicles engine, main engine are basically IC engines, and these are of two types: spark ignition engine and compression ignition engine, or in short we can say SI engine and CI engine. So now we will study about, as we understood what is IC engine. Now we will study air standard Otto cycle. So first understood what is this air standard Otto cycle. Air standard Otto cycle is, by the way, SI engine. This is SI engine, and in this spark plug is used. The spark plug will help to burn the fuel air mixture in this chamber where the fuel mixture are kept. The working fluid in the air standard Otto cycle is air, which is considered to be air, or we assume that it's air, and it behaves as a perfect gas with a constant specific heats. And basically it is used in diesel or petrol engines. This cycle is basically used in diesel or petrol engines. Efficiency formula for this air standard Otto cycle is 1 minus T1 minus 81 upon T2. This is the efficiency formula for the air standard Otto cycle. Now let's see the graph, what it means. This is the PV diagram of this graph. This is point 1, this is point 2, point 3 and point 4. Heat is added in this side and it gives heat from this side. It is added in this side and it gives out in this side. This is the PV diagram of Otto cycle. Now we'll see the TS diagram of Otto cycle. It is added from this side and rejected from this side. So this is PV diagram and this is TS diagram. TS diagram, temperature versus entropy diagram. So as you can see in the graph, in process 1 to 2, basically this is an adiabatic compression of air. We can say S equal to C. Adiabatic compression of air takes place in 1:2. We have 1 to 2, and this is a cycle. From 1 to 2, adiabatic compression take place. From 2 to 3, heat addition at a constant volume take place. And from 3 to 4, again reversible adiabatic expansion. In this case, over here as well, adiabatic expansion take place. Over here take place adiabatic compression. Here compression, here expansion. I'll write it. Wait for a minute. From 1 to 2 is reversible adiabatic compression takes place. And from 2 to 3, heat addition at constant heat addition at constant volume. And from 3 to 4, reversible. We can write adiabatic as isentropic process as well. Isentropic expansion. Then from 4 to 1, this is heat rejection. At volume is equals to constant. So basically what happens, from 1 to 2, isentropic compression will take place, and from 2 to 3, heat addition at the constant volume take place, and from 3 to 4, isentropic expansion take place, and 4 to 1, heat rejection with the constant volume takes place. And same case with the TS diagram as well, temperature versus entropy diagram as well. So this is the Otto cycle. Now we'll be understanding air standard diesel cycle. So actually what happens in this is, in air standard diesel cycle, we can say it's a model of the process that takes place in the diesel engine, and is made up of 4 reversible processes. Actually this is this is specifically made, this cycle is specifically used for the diesel engine only, and it have also 4 processes. But before that, we will make its graph. Spring diagram. This 1, this 2, this 3, this 4. So there's a isentropic process over here as well, and isentropic process over here as well. Heat addition from here at a constant volume, a constant pressure, heat addition, and heat rejection with a constant volume. So you need to remember this: constant volume heat addition and constant volume heat rejection. And again, as I have said, isentropic compression from 1 to 2 is an isentropic compression, and from 3 to 4 is an isentropic expansion. So these are the 4 processes in this. From 1 to 2 there is an isentropic compression, and then from 2 to 3 constant volume heat addition, and from 3 to 4 constant volume isentropic expansion, and from 4 to 1 a heat rejection with constant volume. Now we will study the TS diagram for this diagram. This is like this. This is 1, 2, 3, 4. It comes from here and it rejects here. This is Q. This is Q. It takes in constant volume, and as I've already mentioned, from 3 to 4, when heat is addition takes place, pressure is constant, and when heat is rejected, volume is constant. So this is the TS diagram of the diesel cycle. The efficiency and the net power output of diesel cycle depend upon the several factors, including air inlet, temperature, cutoff ratio, fuel mass, fuel mass, flow rate, and air fuel ratio. So its efficiency depend on various factors like inlet temperature, number one, number two, cutoff ratio, number three, uh, air fuel ratio, and number four, fuel mass flow rate. So the efficiency of a diesel cycle, air standard diesel cycle, depends on inlet temperature, cutoff ratio, air fuel ratio, fuel mass flow rate. And the diesel cycle have compression ratio. Air standard diesel cycle have a compression ratio from 14 to 17, between 14 to 17 compression ratio. And the cycle works by injecting fuel into hot compressed air, which causes the chemical reaction and combustion. As I have said already, this diesel cycle, air standard diesel cycle, is CI engine. Otto cycle is SI engine. Air standard diesel cycle is CI engine. So what I mean is, air standard cycle is CI engine. It means it doesn't have a spark plug. It works like by when the compressed hot air is come in touch with the fuel, it automatically get combusted due to the kinetic energy of the fuel molecules, gas molecules within the air particles, which further automatically combust the combustion process. Chemical reaction will automatically take place. Combustion process is relatively slow as piston moves outward and combustion takes place. As compared to the SI engine, combustion takes place in very relatively low speed. So this is the air standard diesel cycle we have talked about. Now we'll see dual cycle. Now we'll talk about the dual cycle. Excuse me. Now we'll talk about the dual cycle. Now we'll talk about dual cycle. So, what is dual cycle? Actually, it's not only a dual cycle, it's an air standard dual cycle, and it's a thermodynamic model that combines the Otto cycle and a diesel cycle methods to model a real engine profile. We can say it's like a help to make the real engine profile with the help of combination of Otto cycle plus diesel cycle. This both helps to make the dual cycle. Air standard dual cycle is a thermodynamic model that combines the Otto cycle and diesel cycle method to model a real engine profile. So, which further helps to make the real engine model. So let us make the graph and understood its process one by one. So let's first make PV diagram. By the way, mark my words, it's a air standard dual cycle. So it's PV diagram. So 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5. So if you look carefully, so what happens is, in this cycle, again from process 1 to 2, adiabatic compression takes place. As is equals to C, adiabatic compression or isentropic compression takes place from process 1 to 2, and adiabatic expansion takes place in process 4 to 5. Over here, isentropic compression, expansion or adiabatic expansion takes place from in 4 to 5. Heat addition takes place in 2 to 3 and 3 to 4. Heat addition takes place from here and heat release from here. But mark my words again. Heat rejection is at constant volume, and heat addition from 3 to 4 is at constant pressure, and heat addition at 2 to 3 is at constant volume. So this is the thing we need to remember. From process 1 to 2, it takes isentropic compression. In process 2 to 3, heat addition with a constant volume. From process 3 to 4, heat addition with a constant pressure. And from process 4 to 5, isentropic expansion. So this is a PV diagram and its processes. Now understood. Let's understand its TS diagram. This is its TS diagram. This is its TS diagram. This is 1, this is 2, this is 3, this is 4, this is 5. So, as I've said, in process 1 to 2, we can say adiabatic compression and a heat addition takes place at constant pressure. In this graph, you can directly mark like 1 to 2 is constant pressure, 5 to 1 is constant volume, and from 3 to 4 is constant volume. So this is TS diagram of the dual cycle. This is the combination of Otto cycle and diesel cycle. So thank you very much for watching this video. If you have any doubt, you can surely ask me in the comment section, and if you can, please like and subscribe my channel. It will help to grow my channel. Thank you very much for watching this video, and have a nice day ahead.